Hey guys, welcome to the stream. So as you know already, in the last stream we completed all the projects of Nand2Tetris Part 1, and I have already started watching the Nand2Tetris Part 2. I have completed the first week videos. And for the first week we have this project. We are going to build a virtual machine translator. So we'll build a translator in Python that will translate this virtual machine code like this one into the equivalent assembly code. So this assembly code is the same as before, but this VM code is new. And again, this VM code is just an intermediate code which will be compiled from the Jack language, which is very similar to Java language. Stack arithmetic, what do we have inside memory access? Okay, so these are all the test file which we'll be using later on when we build this translator. So let me create a Python file. Let me call it VM translator. Yeah, that will be all right. VM translator. Let me capitalize VM. VM translator.py. Okay, so let's see what we have to build exactly. We have this kind of instruction: push, sub, add. So let's review this VM code language first of all. So as you can see, this Jack is supposedly a programming language which is written by this course instructors, and this Jack will be compiled using the Jack compiler into a VM code, and this VM code will be translated into the machine language, or I should say the assembly language, hack assembly language, which will be running on the computer, the hack computer that we built. So for this project we are going to build this VM translator which will translate this intermediate VM code into the hack assembly language. So this VM code is built using this I don't know what it is, but what I should call it, stack machine architecture. Yeah, so it is built using stack machine architecture. And suppose if this is the higher level command, it will be compiled down to this kind of instruction in the VM language: push, add, pop. And inside this VM code we have 4 types of instruction: arithmetic, logical, memory segment commands, branching commands, and function commands. So for this project section, which is project section 7, we won't be worrying about branching and function commands. We will just implement arithmetic, logical, and binary memory segment commands. What I mean by that is basically we will build a translator which will translate this arithmetic, logical, and memory segment commands. And in the project section 8, we will be also creating a logic to translate branching and function commands. So these are the kind of arithmetic commands: sub, add, are 2 kinds of arithmetic commands. But I think this push is a memory segment command, I guess. Or is it a part of arithmetic commands as well? Yeah, so this push commands are memory segment commands. So let's review this arithmetic commands. So we have this kind of stack, and we can push values onto the stack, and we can also pop the values. And the stack data structure is like that you can only push the value on top of it and pop from top of it. You can't push or pop at the end of the stack. So this is the top and this is supposedly the bottom. So let's say if we push 2 to the stack, then it will come over here. After that, if we push x, which is, it stores 7 as the value, therefore we'll have 7 on top of 2 afterwards. So as you can see, it grows like this. And when you pop, so if we now check this subtraction command, what it will do is 2 minus 7. When we push 2 values onto the stack and execute this subtraction command, it will take 2 values from the top of the stack. This will be the first one and this will be the second one, and it will do this value minus this value. So 2 minus 7 is minus 5, and it will pop both of these values and push their result onto the stack. So that is the sub command. After that, we also have add command. So let's see how it works. First we push y contains 12. Okay, first we push 2, then we x. Okay, this is the state after these 3 commands. Okay, this is the state right now when we push y. So we had this -5 from this command. After that, when we push y, we have 12 on the top of the stack. We again push 9. So the stack will become -5, 12 and 9. And after that, we execute the add command. So this add command will add the top two values, 12 plus 9. So 12 plus 9 is 21, and it will remove this, or I should say the pop these two values and add and store the result at the top of the stack. So we have 21 now after this add instruction. Again we execute another add instruction, which will again add the values from the top. So -5 plus 21, so the result will be 16. And after that we execute this pop command. So what this will do is pop the top value from the stack. So the stack will become empty because we only had one value, which was 16. So stack is empty now. And when we do the pop, we also store this whatever we popped from the stack inside the memory. How exactly we store and where exactly we store will depend upon the memory segment commands. So this is an incomplete command. We'll see what the complete memory segment command looks like when we come to the section memory segment commands. Alright, so this is basically it for arithmetic. We only have two arithmetic commands, subtraction and addition. By the way, I'm just reviewing so that it will be easier to write the translator, although I have watched the lecture. Okay, so after that we have logical commands. So first we pull the push. We have already seen how this push commands work. So I will skip to the part where we push 7. So this will be the state, and after that we execute this lt command, which is less than. And again the way it will work is it will work on the top two values, but this first value will be the first argument to this less than command, less than operator, and the second, this is the second argument. So it will be like this: 15. It will check for the condition if 15 is less than 7, which is false. So that means it will store false. Again, just like the addition and subtraction command, these two values will be popped off the stack, and we will have the result at the top of the stack, which is false. After that, we will execute again push y and push 8. Y contains as 8 as well. So the state of the stack will be like this one after these two push commands. So what do we do after? We execute the equal to command. This will again check the logic, or I should say the condition for this for the top two values. So 8 equal to 8, which is true. That means it will pop these two values and store the result at the top of the stack. So we have false and true as the two values in the stack. After that we execute this OR command, which will OR the top two values. So false will OR true, which will give us true. So these are very simple commands. So these are all the possible arithmetic and logical commands that we have available inside this VM code. Addition and subtraction. So we only have two arithmetic commands, I guess. Maybe this negation. Yeah, this negation is also a kind of arithmetic command. Yeah, it is arithmetic. So we have three arithmetic commands, and these are all the logical commands: equal to, greater than, lt, and whatnot. Okay, so those were the arithmetic and logical commands. What do we have next? Okay, we now have to check how the memory segments work, which is a bit more complicated than the arithmetic and logical commands, but not that much. So this is the Jack language. So it looks very much similar to Java, and this language will become compiled down to this kind of VM code, for which we have to build the translator. We also have to build this compiler, but that will be for the later projects. Okay. So this kind of assignment and arithmetic operation will be compiled down to this kind of code inside this VM. So we'll have push s1, push y, add. So what's the use of memory segment anyways? As you can see, we have many different kinds of variables. We have this variables which are local to this function. Then we also have this argument variables, and we also have static variables. So for this different kinds of variables, we will have different memory segments, which are virtual memory segments. So yeah, these are the three kinds of variable that I told you: argument variables, x and y, local variables, these are local variables, and static variables. So for those variables, we will have this kind of segments which are virtual. They are not separated inside the original RAM, but I mean not separated as in physically, but they are virtually separated. So we'll have a different segment for argument variables, for local variables, as well as static. We also have more segments which we'll see. So when we write this kind of Jack code, this will compile to this kind of VM code. So you see, that's why I say that there's more to this memory segment commands. Before we only had this kind of command, but now you can see we have push static 0 as well. So what this will do is check the value of static 0, which is this static memory segment, and it will take this value where it will take the value from this index 0 of this static memory segment and push that value on the top of the stack that we previously saw. And again, for this push argument one, it will do the same. It will check the first index of this argument first, as in the 1th index, as the indexes start from 0. So it will get this argument to 1 indexed from the argument a memory segment, and it will push the value on the top of the stack. So we also have a constant memory segment, but it is not actually it doesn't actually have a virtual segment. It doesn't actually have a segment inside memory anyway, because it is totally virtual. And what I mean by that is this arguments local and static will have a particular segment inside the RAM, but this constant won't be having any segment. It is just that when we execute this command push constant 17, it will push this value 17 on the top of the stack. So for that we don't need any we don't need to store any values inside the memory segments. So these are the different memory segments that we have available inside VM code: local, argument, this, that, constant, static, pointer, and temp. And we are going to interact with this different segments using only two commands: push and pop. And the only thing, there are two variables here, segment and I. Segment will refer to one of the segments and I will be the index. For constant, we won't be having pop segment because we don't really have a virtual memory segment for constant anyway, so it doesn't make sense to pop anything from this constant. So suppose if we have this kind of jack code, let static 2 is equal to argument 1. When we translate it to the machine assembly language, it will translate this code to these two commands: push argument 1. So first it will push the argument 1. So what it means is, first it will get the argument 1, which is 12, and it will push. Where is it happening? Let's see. So push argument 1 will get this argument 1, which is 12, and it will push it onto the stack, and just immediately after that it will pop that particular value which we just pushed before, and it will pop it and store it inside static 2. So as you can see, we had 171 before, now we have 12. So this command is executed as it should. Argument, so this static 2 is now storing argument 1, the value which was inside argument 1, which is, so we didn't change actually. So all right, so we have seen the arithmetic logical commands and memory segment commands as well. Okay, so although we have seen the logic, the memory segment commands, there's more to it. So how do we exactly implement inside the machine language? So what does it translate down to? And therefore we will also be using the menu pointers to manipulate the RAM, because these are virtual memory. These segments are all virtual. They don't really have a different physical presence inside the RAM. They are all present inside the same RAM. So how do we exactly distinguish between these different segments, and how do we retrieve and change the values? So we'll see how to do that. And one important thing is to do that is pointer manipulation. Okay, so this is just a pseudo assembly code which will be translated down to this kind of assembly code. So what we are doing first is at P, this is A type instruction, so this will select this RAM 0, and now this M points to this value, and we get this value 257 and store it inside the data register D is equal to M. So this P works as a pointer. Star P means the memory location that P points at, and P contains 0. P is equal to 0, and this is the 0th RAM, and it contains some address location. Okay, so wait, I did a mistake. So when we do at P, what it will do is store the value of P inside the A register. So it will store 0 inside the A register. That means this M points to this value 257. When we do A is equal to M, we change the value of A to 257. So now the address register points to this memory location 257. Sorry, this one 257. And now when we do D is equal to M, this M points to this value 23. So now we store the 23 value inside data register. So as you can see, this RAM, so what it means is this variable P doesn't store exactly a value, but it stores an address which points to a different segment inside the RAM where the value resides. So it is a pointer to different memory segment. So that's basically what a pointer is. And we can also increment and decrement the pointers. So if P is pointing to 257, if we do P minus minus, then this P will contain 256. So it will be pointing to 256 now. So now this data register will have this 19 value when we do star P. Before it was 23 because it was pointing this value, but when we decremented it, it started pointing at this segment. So we can also increment and decrement the pointers. So why is this exactly important for virtual machine code? Because when we have this kind of command push constant 17, what it will do is, or I should say what it will translate down is, so this is just an abstraction, we will have to translate it to the actual assembly language. So how will it work basically? So when we do push constant 7, what we are doing is pushing 17 on the top of the stack. So this is the logic that we have to implement inside hack assembly. First so for this stack we'll be having a stack pointer, and it will contain the address of this stack, because again I want to say that we don't really have a different stack physically inside this machine. We are implementing this inside the same RAM. So this stack pointer will be pointing to the segment where we have this stack. It happens to be at the 258. Sorry, it starts at 256. This is the base address 256, but this stack pointer will always point to the top of the stack, and as we already have these two values L and phi, it will be pointing at 258. So how do we add 17 at this value? First we select that address. So star SP means this segment, and what do we want to do there? We want to store 17. So at star SP, what this means is go to the RAM where this SP pointer points to, which is the top of the stack, and store 17 there. So it will execute this push command. But after we store the value, we also need to increment the stack pointer, because we always want to have the stack pointer pointing to the top where we are going to, where the, or I should say, if we store this something at the top of the stack, we always want to increment the stack pointer so that we can again work with the top of the stack. So after this operation, we have to do sp plus plus. So again, this is just a pseudo logic, or I should say pseudo code, and this is what the actual assembly code looks like for this two, or I should say the push constant 17 operation. So this is what we have to do. We have to build a translator which will convert this type of instruction, which is VM code, into this kind of hack assembly language. So let's review this command as well. What we are doing is first getting the H17 value, because we have to store 17 value, and storing it inside the data register. After that, we select the HSP to work on it, and we do A is equal to M. So A will be 258 afterwards. And when we do M is equal to D, M is pointing to this 258, and D will be having the value 17, which we previously stored. So we store this value, and after that we also need to increment this SP pointer. So what we will do, we will again select the SP pointer, and this M points to this value. So we'll select M is equal to M plus 1. So that's how we implement push constant 17. So now we are checking how this local segment is implemented inside the hack assembly. So for local also, just like stack pointer, we'll be having a base address, which will be a base, which will point to the base of this local segment. So this, suppose we have LCL is equal to 1015. So this is the base address of the local segment, meaning it starts from this. So before, for stack pointer, this always pointed to the top of the stack, but now for this LCL, which is the local pointer, we don't have a pointer which points to the top of the local segment, but it will be pointing to the base of the local segment. So it doesn't matter however many values we have inside this local segment, the local pointer, LCL pointer, will always have the base address. So it won't be changing, at least for the execution, or during the execution of the program. So when we do a pop local I operation, what it will do is pop the value of the top of the stack and store it inside local I, and I is the index inside the local segment. So how do we implement inside this? So this is the logic. First we select the address. So what is the address? It is the base pointer plus whatever I is. So suppose I is 2, that means go to the base address of this local segment and increment it by 2. So this will be the RAM address where we have to store the value for this instruction, pop local 2. So that address will be selected and stored inside a variable ADDR, and after that we will decrement the stack pointer. Why? Because we want this value. And after that we will do add address. So this address, wherever this address is pointing to, store there the value where this SV is pointing to. So this SV is pointing to 5 after we do decrement, and we don't need to remove this 5. So this is what we only need to do inside the logic of assembly. Why? Because we don't really care if this value exists or not, this 5, because as far as we are concerned, when we decrement this stack pointer to this position, this value is as good as gone. We don't really care, so it becomes garbage, which will be overwritten anyway. So this will be the logic for pop operation on the local segment, and this will be the logic for push operation. And again, this is the pseudo code, and we will have to write a corresponding hack assembly code. So we also have this argument segment, and this and that. This and that are a bit different. So high level operation on the field variables of the current object are translated into VM operation on the entries of the segment this. So this will be for the current object. So this is specific to object oriented languages. So this check is just like Java, therefore we also have object oriented associated design, I guess. And this that is for array entries. So just like we did for push pop local I and local segments, the same applies to this 3 segments as well. So push pop operation on all of these segments will be similar. We just have to change this segment pointer, and yeah, that's just it. We just have to change this segment pointer to the segment which is described inside this segment. Just like LCL, we will have base address for arg, which is the argument segment, and this and that segments. What else do we have? We have constant now. So for constant, we don't have a pop operation, we just have push operation, which will be just like this one. We already saw it earlier. Okay, what do we have after that? We have a static segment as well. So for static, the code is a little bit different, because for static we don't have a particular segment inside the memory, but the static will be converted to this kind of assembly code. So whichever static command is executed first will be converted to this variable who is the name of the file, and .phi is this file, the value we are storing, and this will be stored starting from address 16, and these are all for the variables of the program. And we have this segment because they should be seen by all the methods in the program. After that, we also have a temp segment. So for temp, we have a specific segment which will be starting from 5th up to 12. So we only have 8 registers for this temp segment. So this will be the corresponding pseudo code, 5 plus I, 5 plus I. And because we have a specific segment starting from 5, we don't need a pointer. We can directly write 5, which will be the base address of this segment. After that, we have this pointer, which is the last segment. So this segment stores the base addresses of this and that. 0 pointer 0 will store the base address of this, and 1 will store the base address of that. So now that we have seen this type of all two types of arithmetic, logical and memory segment commands, I think we don't need to review anything anymore. So let's get into the code and start coding the translator. So what we'll be needing: the author suggested a particular architecture, so let's see what he suggested. This is the final thing which we want. We will be getting this kind of code as input to this program, and we'll be outputting this kind of file which will have this assembly code. So this is the proposed design. It says that we should create this kind of different classes, or I should say the modules, one parser, one code writer, and main. This parser will parse the VM commands and get the individual terms, components of that particular command, and this code writer will write the corresponding assembly code into the file. We'll have .vm file as the input, and we'll produce this .asm assembly code file as the output. So this is the plan. We have to construct a parser, then a code writer. So let's start writing. Okay. This is how we call the main, right? Let me see. Yeah, if name, sorry, it's not in it, there's name. Destination name. So what we will be doing inside this main, we'll be working with the command line arguments. So let's get the system module. Open it like this. How do I yank from one file to another? Copy from one file to another in V. they're suggesting to open the file like this. This is how we open the second file to copy the lines. It's saying that just give me this error message, so it's the problem. Start frame and open file 1. Yeah, I already have a file 1 opened, and using this command, the file you want to copy, but it is not opening it. Okay, what if I open this file inside? So what if I do this 07 and the file name is VM. Oops. Okay, so this methods don't really work. Open both files in a split window and navigate between them. Within the first file, Control W. What does Control W does? Okay. It doesn't matter. Let me write the command. With open, so we have to open sys dot. What's the command? It is sys dot argv. Sys dot argv, and the file will be passing for reading will be inside the first index, and this will be the name of the file, and we are opening it for reading, and this will be the VM code, so call it VM. Let's first for inst in VM print the instruction. So let's see if this works or not. Dot VM translator, and we'll be passing stack arithmetic simple add VM. Yes, so we are getting the output. What else do we need to do? So now that we can open the file, we'll have to write a parser class, and what this will do is it will get the individual commands. It will be very much similar to the parser that we wrote for the assembler, so I think I should copy it from here. So we created a parser command, we did init and all that stuff, because inside this parser also we wrote the logic for cleaning up the commands and stuff, so we can use it. I really want to know how to copy this stuff. Why is this not working? Oh, hey man. Yeah. By the way, do you know how to copy from one file to another file in Vim? Because I'm trying to copy it using this method, but it is not opening it up. Okay, all right. GG. You mean GG command? Well, GG goes to the starting of the line. So I'm trying this command E, but it is wait, this time it is giving a different. All right, it opened it up now. So after opening it up, I can select the parser, can yank it, B1, and paste it. Yeah, great. So this worked. So I was trying this same command before, but it was not working, but somehow it worked this time. And now my key binding is not working. I will have to reload this game, I guess. By the way, do you work with Python? Alright, so where was I? I need to translate this kind of commands into the assembly code. And let me clean up this class. I don't need this. And I won't be needing this values type. I guess we'll be using type, but yeah, we're needing the check type as well. So let's first clean up the cleanup method. So inside this we'll get the instruction and strip it, and we will also remove the commands. What kind of comments do we have inside this VM code? All right, so the comments are similar. It starts with forward slashes, so this method will be similar as well. Okay, so we don't need to modify the cleanup method. And let's review the check type method. First we are checking if the instruction is empty, then we return nothing. And if it starts with @, so now we don't have this kind of commands which starts with @. Instead, what kind of commands do we have? We have push, pop, addition. So We'll see how to use this check type method later on, but for now let's use the parser to parse the instruction. Get the parser in P, will pass the instruction. And now we can print the instructions. Let's see if this works or not. All right, so this kind of this kind of file is now cleaned up and we are getting this output. So we have removed the commands and all the unnecessary stuff. Now we need to parse this individual statements. So how are we going to do that? Okay, let's see what we need to do. Reads the VM command, passes the command into its lexical components and provides convenient access to these components. Okay, so we do need a command type, and this will be the type of command: C arithmetic, C push, C pop, C label, C go to, C if. All right, for now we'll be having just three types: C arithmetic, C push, and C pop. We won't be worrying about this other command types. So let's write the logic for this command types. If it is an empty line, we will be returning nothing. But if the instruction starts with let's say for, we are on the slide 108. If the instruction starts with either add, or we also have instruction starts with add and sub. We also have negation. So for this type of commands, we should return C arithmetic. C arithmetic. If the instruction starts with either add, sub, not and, this should be or. So if the instruction either starts with and, add, subtraction, sub, or negation, then we should return C arithmetic as the type. And also if it starts with let's see, for with push, do we have a capital push or no? We have lowercase commands, so this should be lowercase push. Or if it starts with pop, then we should be returning C push. Wait, we should be returning different types for push and pop, so this should be in case of pop we should be returning C pop, and if it starts with push we should return C push. And if it doesn't start with any of this, well, for now we will be having only this 3 types of commands. If it is either empty, or it will have push or pop, or the addition and subtraction or negation. Oh wait, we do have the logical operations as well. We are not given the command type for logical operations. We have C push, C pop, C labels. Okay, that means the method is going to be a long one. We have to take care of this logical commands as well. Equal to, greater than, less than, and or not. So let's copy this, and if the instruction starts with EQ, that means it's an equal to command. So in that case, what should we return? But well, let's just return EQ. If it starts with wait, shouldn't we also return different types for addition, subtraction, and negation? Let me think. So where are we going to use this instructions types anyway? So we'll be using when we get this equivalent codes. So yeah, we should have different types for all the different commands. Then why have they given only C arithmetic? And that's the passing of reads the VM command, passes the command into lexical components. C arithmetic is written for all arithmetic and logical commands. Why is this only written? Because if I recall correctly, the assembly command for different arithmetic commands will be different. For addition, we will have different commands. Okay, let's check the assembly language and see how we implement the logical and the arithmetic operations. We have the computation for that. So we will be using the C type instruction for arithmetic and logical operation. Let's check the C instruction types. So what we'll be having for addition, we'll pop the two values of the stack, and in case of addition we'll add those. In case of subtraction we'll subtract those. But if we are just returning the C arithmetic, how are we going to distinguish between these different operations? Because at the end we do have to implement this different logic. So if we check this, let's check the arithmetic operations. Memory sequence would show these are the arithmetic. No, these are not. Where are the arithmetic operations? So this will be the kind of VM code we will be having. So we'll have push operation and either a logical operation or arithmetic operation like add. So how do we translate this into the machine equivalent machine instruction? For push operation, we'll take care of it later on, but for subtraction, let's see, what do we have to do for subtraction? We'll get the first two values of the top of the stack and subtract the second value from the first one. So to carry out this operation, we'll use a C type instruction. It doesn't matter, we are going to return the individual types. So for addition, we'll return C add. By the way, why the hell are we adding this C anyway? Shouldn't we directly return arithmetic pop push? Let's read the documentation again. I'm really confused because the documentation is somewhat cryptic. Where is it? So this is what they are suggesting. What this partial should do. It should get a VM command, which we are getting inside this instruction variable, and it should return a command type, argument 1 and argument 2. And they are suggesting that we should return C arithmetic for all the arithmetic and logical operations. Wait, what are they saying over here? Returns the first argument of the current command. In the case of arithmetic, see it, command itself, add, subtract, etc. is written. Should not be called if the current command is C written. All right, I get it. So in the case of, so what they are suggesting really is, this is the general or overarching command type. So when we return C arithmetic, it is a general command type. But when we call this argument 1 routine, in that case, it should return the different arithmetic operation which is specific to that instruction. So this argument 1 should return addition or subtraction or whatever it is. So I guess this implementation is correct. So let's do that. So for addition, subtraction and negation, we are writing C arithmetic, and for the logical operations as well, we should be returning the same C arithmetic type. So we should get rid of this indifferent condition, because this should be, by the way, instead of using this in self.instruction start with, we should write a list which will have this different terms: addition, negation, and subtraction, and we should check for if the value is inside this instruction string or not. So let's see how we can implement it. Strings, we should use a particular method. Searching the string for a value. Okay, Python, how to check if string from list is a substring of a string. Any substring in string for substring in string substring. If any of the substrings in substring list is contained in string. So I suppose this is the list, substring list. What is this string dot contains? So I guess this string is this instruction in our case. So let's try to use this any. So before we do that, let's create a substring. So for arithmetic, we will create arith list, and the first entry will be add, second sub, third should be negation. Then we have the logical operations. So which are those? 1 0. Alright, so these are the logical operations. We have EQ, greater than, less than, and, or, and not. So now let's use this command. So I guess this string is self.instruction. So for this I should, let's write another condition. If any map, and this string should be, I guess, self.int dot contains, and we'll pass the arith as this substring, and this should return true if the instruction has any of these terms inside the instruction string. And in this case we will be returning, so let me comment out this. In this case, we will be returning c arithmetic. So let's get rid of this commands. Now let's check if this method is working or not. So to do that, let's print the type as well. For empty lines, we are getting none as the type. For this, we are getting C. So this means, wait, for push and for this to push commands, we are getting C. That means the condition is not. Alright. So this is correct. For addition, we are getting C arithmetic. So that means our logic is working. For addition, we are getting C arithmetic as the type. Now for this kind of commands where we have push and pop, what should we return? Let's see. Let's go back to slide number 10. So for push, we should return C push, and for pop, C pop. So now let's write the logic for C push and C pop. So now for C pop, we can use the logic that we are using previously. C instruction starts with, if it starts with push, the type should be C push. And if the instruction starts with pop, the type should be pop. Alright, and again, we don't need to take care of this return types label go to. We will be coming back to those types later on when we build the project 8. So for now, this types will be enough. So if it is an empty string, we'll be returning nothing. Let's get rid of this. And if it is inside this list, then we'll return C arithmetic. And for push, C push, and pop, C pop. So now we do have this routine. Now let's write a method for getting this argument for what this should return. First argument of the current command. In case of C arithmetic, the command itself add, subtract. And what if we have push and pop? In that case, I guess we should return the segment part. So let's write this function. Right, what should we call it? Let's call it arg1 get arg1. Right, so it should return the first argument. So that means we'll have to parse the instruction and get the second part. But in case of, so this parsing will depend on the type. So let's see what we should do. If self dot type is equal to none, in this case will return, okay, like should not directly return it. Let's get a variable self dot arg1 and it will be none by default. And in this case we will not return anything. else if self dot type equal to C arithmetic, then we should return, let's see, C arithmetic. That means we will have add. Well, in this case we should return, what the hell, why is this indentation messed up? All right, it is correct now. All right, so in this case we should return the whatever is inside the first term. So we won't be returning directly. We'll first get the self.arg and we'll parse self.instruction. We will split it on the space, so this will give us, well, if it is a C arithmetic type, we don't even need to split it because we know that this arg1 is the first term, so we can directly pass self.int to arg1 and we'll return this self.arg1. Now what if the instruction is of type C push? Well, in case of C push and C pop, the logic will be similar. So let's copy this. Or self.type is equal to C push or C pop. Then in this case we do need to split the string, so we'll split it on the space, and the first 0th element will be the either the push or pop term, second element will be the segment, and third element will be the index. So we should get the second element, which is on the first index. It will be the arg1. So we have taken care of argument 1 as well. So let's see if this function works or not. Get arg1. Let's call it for all the instruction types. P dot get arg. Okay, so for this we are getting constant, this argument. For this again we are getting constant, second argument, which is actually the first argument. And for addition we are getting addition. So yeah, this method is working correctly as well. Okay, argument 2. Now this argument 2 returns the second argument, and this argument will be called only for C push and pop. Let's write get arg2. If the self.type is equal to none, will return nothing. If it is C arithmetic, in this case also we should return nothing. don't need to write the logic anyway, because we only care about C push and C pop right now. You can write this self.type is equal to C push or C pop. In this case, we need to return, well, let's just change this to 2. So this will give us the second argument. Let's change this as well, and let's get another variable arg2. Alright, we have this method as well. Let's check if it works or not. Right, in this case we are getting, wait, we are not even calling it, so let's call it. So for this push we are getting 7, and for this one we are getting 8, but for addition, oh wait, why are we getting none for this operation? Oh, of course, because this none is for the second argument. Yeah, so it is correct. Okay, what do we need to do now? Let's get rid of this method, we don't need it. So I think this is it for parser, at least for now. So we'll try to write this class code writer. Let's start definition class code writer. It should open up the output file stream and get ready to write into it. Okay. So whenever we call this code writer, it should open up a file. So let's get the logic. Okay, I need to copy the command for writing. Yeah, I need to copy this command. That's what we need to do. We have opened the file for writing. Now in this case, we won't be giving it .hex extension. The extension type should be .asm. So let's change this as well. What this will do is get the argument. We'll just get the name, the name from the command line argument, and it will add, just get the name and remove the extension, and it will add the extension .asm and open this file for writing. Okay, so after that, wait, should I open this inside this init function? Because I also need to close it. Yeah, we'll see. So let's see what we need to do inside code writer. So what we are doing is getting the instruction and translating it. So we'll write this write arithmetic function, which will take the command and give us the equivalent machine or assembly code. So before we figure out how to open the file, let's write this function. Write arithmetic will pass the instruction. Well, we won't pass the instruction, we'll pass an object of type parser. So that we can get the arguments, we can access the argument methods. So let's see, parser. What we will do inside this, we'll first of all have to check for the type of the argument, right? So how do we change? If parser dot type equal to, wait, no, yeah, we should check this one first. If the type is arithmetic, well, we should check for if the type is not arithmetic. If the type is not arithmetic, then return. But if the type is arithmetic, what do we need to do? We need to get the argument 1. So we'll have to implement this slowly because there's a lot involved. And before we write the equivalent assembly code, we'll have to implement this, how to open the file for writing. Well, let's not open the file for writing right now. Let's worry about writing later on. Let's just see if this code writer works or not. So Okay, let's see what we need to. Now this arithmetic operation, let me open it up in another window because it's very hard to scroll again and again. Addition, subtraction. So let's try to write the logic for addition. So it should be something like this. If we have add, what this should do is first get the two values from the top of the stack. So how do we get two values? So we'll select the stack pointer. After that, the stack pointer will do a equal to m, and after that, now this m should have the value where wait, no, before we get this, we should first decrement it. So we should first do m is equal to m minus 1. So what this will do is decrement the stack pointer. So if the stack pointer is here, what we will do is change it to here. First stack pointer will be having at sp. So select at this. Now yeah, this is correct. And after decrementing it, what we need to do is get the value pointed by this. So we'll store the value inside D. This will be the first value. Wait, what are instead of getting this kind of commands. So let's see. When we get the value inside D, we'll have to get the second value. So we'll again get the stack pointer and decrement it. And we'll do A is equal to M. Now this will have the second value. Now what should we do? Now at that position we should write M is equal to this M plus T. Okay, so now we have executed this operation. So this will be the commands that we have to fire for just for this addition operation. So we'll have to write the logic for the same now. Now if parser dot instead of get, let's just call it arg2, and this one arg1, and we'll also have to change this arg1v arg2v. We need to change arg1 to arg1v. Okay, so let's see. So now I can do parser dot arg1 to get the first argument. If it is add, then in this case we should get this commands. So we should write this commands. So how do we do that? Is as of right now we are not writing it inside a file, so should I create a list? What if I store this commands inside a list? Will it work? Yeah, let's just store it inside a list. Add C. This will be the commands for add C. So if parser dot argument 1 is equal to add, then for now we'll just do well, let me think, is it still the right way? Should I write this function as the inside a list, or store it any different way? What if I just store it as a single string? Yeah, I guess a string will be much more better. But a string is a array anyway. Yeah, for now let's just use the list comprehension. But after that, so suppose if I write it inside a single string, then well, let's see. Let's check I didn't change. So DMs. Well, instead of space, let's use a comma as a separator. That way there won't be any bugs. So let's separate space with a comma. Yeah, this is better. So now what we can do is we can just print add C, but before printing it, we'll replace the comma with a new line character. So right, let's see if this works or not. First we'll get a code writer. So what I will do is check if not P dot, the heck am I doing? Arg 1 equal to, we have wrote command just for add, so we'll write this. In this case we'll let's get the code writer anyway. Code is equal to code writer, and we are not passing anything, so we'll just do this. And after that, or we'll call code dot write arithmetic arithmetic, and we'll pass the parser. So we'll pass the P. Okay, so let's see if this works or not. Expected an indent block. Is it not indented? Okay, it's complaining about this thing. Okay, now fine. What the hell? Why is it still complaining? I have indented it properly, isn't it? Okay, wait, do I have to write pass? I think the indentation is messed up. Oops. This should be why do I have this many errors? Definition.main has error as well. Why? It was working previously. Okay, wait. It may be because this thing is not indented properly, maybe. Why is it complaining about invalid syntax? What did I do wrong? Did I write this class incorrectly? Let's see. Let me try to get rid of this class first of all and see if it works then. Yeah, it is going to complain about this thing now. So let me try to comment out this code. What the hell? Each and every indentation is messed up. How about now? I think there was a how to fix indentation error in Vim. Python. Set tab, retab. Okay. Did it fix now? Let's see. Is this properly indented? Yeah, I think it is. What did I do wrong which messed it up? We try to open it up in Visual Studio Code. Maybe it will fix it. The heck? Let me try to find it. Oh, I get it. Because of this empty method. So wait, I also have an empty method, right? No, I don't have an empty method. Oh yeah, I get it. It's because of this one. Right. So let me try to get this now. Do I have an empty method here? Well, this init is an empty method. Is it complaining because of this init? Let me try to get rid of this command. Still it is giving the error. Where's the problem? Where am I? Okay, yeah, I know where I missed a parenthesis. I missed a parenthesis over here. Okay, so now this will work. So let's uncomment this one. All right, we are getting the output now. Okay, I forgot what we are doing. Okay, so when we encounter an add instruction, we are writing the corresponding assembly commands. So this is the correct output. This is what we want. So we wrote the commands for addition. Let's also write it for subtraction. So let me copy this. Well, instead of copying, let me write it over here only. So for subtraction, what should we be doing? For subtraction, the commands will be similar. So let me copy this. The only change will be happening over here. Instead of m is equal to m plus t, we'll write m is equal to m minus 3. So this will do the subtraction of the two elements from the top of the stack. So let's copy this and call this one sub c, and over here instead of addition, let's give subtraction. And if the parser.arg1 is sub1, we'll do sub c but we don't have any subtraction commands, so the output will be similar as before. But I know this will work. So we have wrote the commands for addition and subtraction. Let's write the command for negation as well. It will be a bit different. So for negation, we only need to get the first element from the top of the stack and change it to negative. So we still need to get the let me copy this and I will modify it. So we still need to get the stack pointer top, and we need to decrement it and get the value inside the D, and again we get the stack pointer. Now what will we need to do? Let's check the instruction type C instruction. We do have negation minus D, so that's what we will do. First we get the stack pointer, then we decrement it and get the value inside the A register, and we store it inside the data register. Again we get the stack pointer, we need to get it again? We already have the value inside data register. Well, instead of getting inside the data register, I can directly do m is equal to minus m. Therefore, there will be no need to do these steps. Wait, but I have left out something, I guess. In case of addition, let me check. After doing the subtraction and addition, again we need to increment it, right? So first we are getting the stack pointer, then we are decrementing it, getting the first element, A is equal to minus A is equal to m, D is equal to m. But now the stack pointer is pointing at top, so we'll get this, again decrement it, get A is equal to m, m is equal to m plus d. After doing this, we again need to get the stack pointer and increment it, m is equal to m plus 1. This step will be the same for subtraction. Yeah, well, I think this is correct. I'm just trying to check an example for this. Yeah, so this example works. In case of subtraction, what we'll do, or addition, stack pointer is over here, right? So the basic idea will be, so let's write the pseudo code. I'm just trying to make sure that we have correct code. So pseudo code would be something like this. SP, first we will do SP minus minus. After that, we store the star SP inside the data register. Again, we will do SP minus minus, and we will do a star SP is equal to star SP plus the value from the data. After that, we also need to increment it. So this is basically the logic for addition. So for SP minus minus, we have this operations. As for first we are selecting at SP. This will give us the address of SP where SP is stored, and we'll do m is equal to m minus 1. So this will change the value of stack pointer. It will decrease it, and after we decrease it, we want to store the value where the stack pointer points now inside the data register. So for that, we'll do a is equal to m. What this will do is a will point to where this stack pointer points. So the stack pointer points to this new value top of the stack, and we'll do d is equal to m, which is basically this step. After that, we again get the stack pointer and decrement it, and we get a is equal to m, and we do m is equal to m plus t, which is this step. And after that, again we get the stack pointer and increment it. So yeah, this is correct now. Now let's see for the negation. So for negation also, let's try to write the pseudo code. So what we'll do for negation is, first we'll decrement the stack pointer. After we have decremented it, we will do star SP is equal to star SP. After that, we will increment it. So this is the logic we have to implement for negation. For that, we will first get the stack pointer, decrement it. Now for this step, we get a is equal to m, and we do m is equal to m minus m is equal to minus m. This will implement this logic, and after that again we get the stack pointer and we increment it. So let's write the steps for neg command. sp m minus 1 a is equal to m. This is similar. So now let's get rid of sp m is equal to m minus 1, a is equal to m, m is equal to minus m. Okay, now let's write the condition. So if pass dot argument 1 is negation, we call neg c. Let's try to run this program. Okay, let's see what we have to do now. We have taken care of the arithmetic operation. Now we need to take care of the logical operations as well. And as we are distinct, or I should say we are classifying the logical operators, logical operation and arithmetic operation as C arithmetic. Therefore we have to write the logic inside this method only. So let's write the logic for less than equal to. For LT, it will be something like this. What we will do, well, it will be similar to the addition and subtraction. So let's copy this addition. We still need to decrement the stack pointer and get the data, and we again decrement it, get the data, and in this time we don't compute anything. Wait, we do need to compute it. So let's see how do we do less than n. How do we implement less than? Well, I think I can use JL this jump commands this time, but what will it look like? See, first I will decrement the stack pointer, then get the data of the second element, then again decrement it. This will give me the data of second element. Now I want to compare the this element with this D. Yeah, I know what we can do. Can subtract it, but I don't need to store the value anywhere. So in this case, I won't be passing any destination. We'll just subtract it, but I will still need a jump instruction. So I will use JLT. So I should have some condition like this: if equal to 0, no, wait, I want to check if this first SP is less than D. If it is less than D, then this will be less than 0, right? So if this is the case, I should store star SP. I should store true. Else star SP should store false. But wait, we can't store true or false. But we can store 0 and 1, right? Even if we can't store true and false, but those won't be the values. So how are we going to implement the negation or the logical operators even? So should we store 0 and 1 then? Well, I guess so. We should store the zeros and ones because we don't have boolean values inside this assembly language. Have they given any hints or something? Let's check. I don't think they have provided any hints. Okay, let's just store 0 and 1 as true and false. So we'll store 1 for true and 0 for false. After doing this, we again need to increment the stack pointer. So let's now translate the pseudo code into the assembly code. So to do sp minus minus, we select the sp, do m is equal to m minus 1, and to get sp's value inside d, we can do a is equal to m, d is equal to m. So now again we do sp minus minus. Now we have to implement the logic. So what will be coming over here? I know we should use a C type instruction. Well, let's see, we can do this. So first we get the computation. So I have to do star sp minus t. How can I do that? Let me check the add instructions. So to do that, a is equal to m, so to do this I have to do a is equal to m, and now a points to that value, that address. Now I can do m minus d. This will be the computation, and for the jump I should write jlt. What this will do is, if m minus d returns the result which is less than t, wait, there's a problem now. Because I need to jump, I have to store this address inside a different variable. So instead of storing it inside a, say I get a different variable at what should I call it? X. Yes, X. Let's call it X. And now I can do a is equal to m. So this X will have the first value now. Wait, no, this isn't correct. Should get X after this, and now I can do m is equal to wait, this is complicated. What I want is this x variable should have the value where this sp points to. Now this sp has the sp is just a pointer, so now I want to check where this pointer points to, so I get it inside a. Okay, so seems that I will have to use two different variables for that. I will have to use two different variables, x and y. Let's get y first. Now I can do m is equal to b, so we'll have the value y value inside the y variable. Now I can do the same thing over here. d is equal to m. Now let's get x, and I will do m is equal to d. We have both x and y values. What do we need to do now? Both values are inside x and y. As we already have this x value selected, well, I don't need to store the value of x, right? Now I want to do x minus y. We already have the value of y inside y, but first to use it I will have to select it. Which one should we select first then? This d still contains the value of x, so now I can select at y. Now this m points to y, so I should write m over here and d over here. So this will do x minus y because this d has x value. So now this is the thing, we don't need this x variable anymore because we are anyway getting the value inside d. So let's get rid of x. So let's walk through it again. First we are getting the stack pointer, we are decrementing it, a is equal to m and d is equal to m. This will give us the value of y. So we have value of y inside d. Now we are getting the y variable, and inside it we are storing the value which was inside d. Now we again get the stack pointer, decrement it, and get the value of x inside d. Now this d contains x value, so now we can select the y. So this m will point to the y value, and d already has x value, so now we can do x minus y. Now let's see what we need to do. This computation will result d minus m. So if d is less than m, which is x less than y, that means the computation will result less than 0. That means we have to check for JLT, which is j less than 0. Jump is less than 0. Now where do we need to jump if less than 0? Let's create a label and we'll call it, oh wait, we do need x. Why did I get rid of x? We will be needing x anyway, so let's call this label let's call it LT, and we will jump to this step LT. And in this case, what do we need to do? Right now the stack pointer points at the x value, so we'll have to get the stack pointer, and at that position, so first we get a is equal to m. Now I can do m is equal to 1, so 1 is for true. But if this is not the case, then we want to store 0 at this position. So let me copy this. This will be for not less than, so NLT 0. So if this condition is true, wait, we have a problem. We don't really need this label, but still we need to jump to LT. So for that, before this instruction I have to write at LT, but that means we'll lose this m, this y variable. This is problem. So should I store the computation result somewhere? Since I have to create another temporary variable to store the value of the computation. Wait, what if I store the value here only? Yeah, this will work. So if I do this, m is equal to, wait, this m points to y, so we'll store the value inside y, but we don't want to do that. I want to store the value inside X. Yeah, it doesn't matter, let's store it inside Y. So M is equal to D minus M. This will store the result of this computation. M is equal to D minus M. So D is X and M is Y. So this will store whatever will be the result inside M. Now after this I can get the LT label, and instead of checking for J and jump this list, then equal to over here I will check it after this instruction. So what am I going to do? Well, alright, instead of storing inside this, I will store it inside the data register. Yeah, this will be better. D is equal to D minus M. Now I can do compute D, and if jump if less than equal to, so if D contains negative number, then jump to LT, and this will store 1 inside this M, or else it will store 0, and after that we will increment the operation. So yeah, we have implemented this logic. So far this seems valid. So let me copy this commands. Damn, there's a lot to clean it up. Let's use new line with comma. Yes. New line and space. Can I select the white space like this? This is going to be messy. This is for less than. Okay, we have a string for less than as well now, but this is just for less than. We still have to create for different. Well, it won't be that much different, I guess. Let's see which other operators we have to get. We have got LT. We still need equal to, greater than, and, or, and not. So let's write the logic for greater than, because it will be somewhat similar. This is for GT. In case of GT, I only have to check if this is greater than 0. So I think I only need to change this jump JGT. Okay, so I only need to change a few lines, few characters. So let's copy this LT. Let's change this LT to GT. And where do I need to change? Yeah, I need to change this JLT to JGT and this LT to GT. What else do I need to change? Yeah, I guess this is it. So we have commands for GT as well. Let's get it for equal to. EQ. So for equal to, I have to check if this is equal to 0 or not. So to do that, I can use JEQ. EQ. Oops, wait. I need to change this labels. Here I have to write GT. And here EQ. So that we can jump to this label. Okay, before I copy it, let me change this label. This LT should be GT. Okay, now let's copy it, change this to EQ. Okay, now what do I need to change? I need to change this GT to EQ and JET to JEQ and this label to EQ. Yeah, that is it. Let me check. We do have, yeah, we do have JEQ and JGT. We do have JGT and JEQ. Now we need to implement the commands for AND, OR, and NOT. Before I do that, let me check if our program still works or not. Yeah, it is still working. Okay, for AND, what do we have to do? AND operation. Well, we do have and OR, so we can use those. Before we do that, let's copy this. This will be for AND. So let's see how we can implement AND. So we still need to do this SP minus minus and get the D, SP inside D. And we do again SP minus minus and check if we will operate SP. So we'll do AND D. This is what we will do. If SP and D. But now let's see how we can carry out this operation, and I can use this computation and yeah, it will be almost similar. The label should be called AND. We'll jump if instead of doing D minus M, I will do D and M. Wait, but in this case, what should I write as the jump command? What will be the result of T and M? Have they given any example? Let's see. They have not given any example for this. I want an example for AND operation. Maybe it does the bitwise operation. Yeah, it will do the bitwise AND. So if this AND operation will result, okay, so now in this case we don't need to do any jumping. We can directly assign the value, so we can do what we were doing previously in addition. We were directly storing the value inside M, so this is also what we can do for the, so let's copy this. So for AND, I don't need to check for this conditions. Copy this logic. Instead of plus, I only need to do AND. Awesome. So here, instead of doing plus, I will just do AND. So for AND, let's copy this add. We have commands for AND now. For OR, it's same. So this should be OR C. And instead of AND, we will do OR. And we also have NOT. So NOT will be similar to the negation. But instead of M minus M, we will do M. Let's see what we have. We have NOT. Negation. This is not C. Alright, it seems we have created all the Boolean logic. So let's write the condition for the same. This will be for negation, LT, GT, EQ, and, or, and not. LT. GT, GT, EQ, EQ, and, oh wait, yeah, it's all right. GTC, GTC, EQC, and this will be and so or C, and the last one not C. Let me try to translate a different program. First we'll get okay, it does contain different things. Let's the right output to simple add dot out. Wait, okay, we didn't change. Test dot out. Wait, what the hell? Yeah, it is correct. But we are not printing anything else. By the way, let me comment this code. Okay, I get it. Because we are only checking for add. Now that we have implemented all the arithmetic, instead of checking for this, let's check for type C arithmetic. Now this will give us the whole output. So this is the whole program. These are the steps for all the logical steps on, but we still don't know if we have written the correct assembly code or not. So I guess we'll get to test it later on. Wait, we do have test file for individual tests, right? For stack arithmetic. Simple add and simple test, stack test. Push constant add. So let's try to get this function. Stack test, simple add, and let's call this one simple as ASM. This is the code for adding. This will add the 7 and 8. So to test this out, we'll need, okay, what do we need? Which tool do we need really? Let's see how to test this. Yes, let's fire up the VM emulator. Where's the VM emulator? VM emulator. You know what, guys, I will try to test this program later on in the next stream. So I think this is it for this stream. I'll see you guys in the next stream. Bye bye.